Guys, we were so close. We had the dead battery with 3 questions left. Anyway, I think where it cut off was we had decided that Fn would be equal to F cosines. That gives us B. Now the other part was that we know F sine of the angle equals Fg with a plus friction on one side or the other. So it could have been F sine of the angle plus friction equals Fg, or it could have been F sine of the angle equals force of friction plus Fg, because we just don't know which side the friction force was on, so we don't know like how big that applied force was. But luckily, C is saying, okay, I have F sine theta equals Fg plus or minus, so that could have been like friction on this side or friction on this side. That's what the plus or minus means, the force of friction, so B and C were our answers. Some students have determined the gravitational mass of an object and want to compare it to the object's inertial mass. Procedures that would allow them to accomplish this include which of the following? Select 2 answers. So we never actually talked about the difference between gravitational mass and inertial mass. It's actually really, really easy. Obviously, both are masses. Every single experiment that has ever, that physicists have ever done have said that the gravitational mass is equal to the inertial mass. Basically, the difference is gravitational mass is a mass that you find with using gravity, like mass times acceleration. And then inertial mass is a mass that is found using not gravity, like that could be F net equals mass times acceleration. Basically, it is a mass that you calculated without using the force of gravity. So they've already calculated the gravitational mass, so the mass that would use the force of gravity to calculate it. Now we want to compare that to inertial mass. So we do not want to use F equals mg. We don't want to use gravity at all to find the inertial mass. So A, hanging the object vertically from a spring scale and recording the scale reading. Well, if you're hanging it and recording like the spring scale like this, that's just recording the force of gravity. So that's the gravitational mass, not the same thing. B, placing an object on one side of a double pan balance. You know, like these, that's not a good picture, but whatever. And then if you have your mass right here, you just keep adding masses until they're balanced. Again, that is using like the force of gravity balancing out, so that's using gravity. C, attaching the object to a spring of known spring constant and allowing it to oscillate horizontally on a nearly frictionless surface and measuring the period. That would be using 2 pi equals T equals 2 pi squared of m over k. That's not using gravity at all. If you were to go into outer space and take a spring and stretch it out, it would still oscillate whether there was gravity or not. It doesn't depend on gravity. So that would be the inertial mass. Measuring or attaching the object to a force sensor, using the sensor to pull it across a nearly frictionless surface and measuring the acceleration. That would be using F equals ma, this like applied force with no friction. That would be the inertial mass. So these two did not use the force of gravity to find the mass, so that's inertial mass. These two would be actually the gravitational mass, which isn't what they're asking for. Wave this is a snapshot of a wave at a particular instant. So this is a longitudinal wave because we're not getting like crests and troughs like a transverse wave. So this is longitudinal for sure because we're getting compressions and rarefactions. These are like high pressure compressions right here, low pressure rarefactions, and then equilibrium would be like this right here. A is the wavelength. That is true because that is the distance from one compression to another, just the same way from trough to trough or crest to crest would be a wavelength. The number of dots per unit length is the frequency. No, that's not anything. The largest distance between 2 successive dots is the amplitude. No, because the amplitude is relative to the equilibrium. So like this distance between, the maximum distance between, isn't the amplitude because it's how far is this displaced from equilibrium. Well, there's some distance apart at equilibrium, so the difference would be like the amplitude. But it was very clearly A and B. Geologist is using a sensor to record waves in a layer of rock and viewing them on a monitor screen. At one moment, the monitor shows the signal above. It is created by two traveling waves. What can be concluded about the waves? Well, clearly we're getting these like beat frequencies. We're getting beats. So you only have beats if you have different frequencies. So for sure they have different frequencies. Traveling in opposite directions, not necessarily true. Different speeds, not necessarily true. Let's talk about like their amplitudes. So the idea with beats is that you get some constructive, some destructive like interference. And you'll notice that these periods of destructive interference, they don't completely cancel out. If they did, it would look, really not an artist, it would look something like this, where you'd have these like this little section of like zero amplitude where it's completely canceling out. So the fact that we're not getting this essentially zero amplitude right here tells me that when they have the destructive period, like a little area of interference, it's not completely destructive because they're not exactly the same amplitude. So this example would be like if I have 5 and 5, right, that's going to cancel out. If I have 5 and 4 like this, then I'm going to have just a smaller. It's still destructive interference, but it's not canceling out to 0. So that tells me they have different amplitudes, so A and B.